Well, this is Module 5, our last module. I love this module because it talks about information and data and statistics and how to represent it. But the first question you must ask yourself, or a student needs to understand, is what graph should I use? So let's have a quick squiz at this one.
Welcome to Moo Math and Science. In this video, I'd like to talk about which graph do I use? There are lots of different graphs that you can use in math and science, and sometimes it's hard to figure out which type I should use to display data. Here's a nice chart that goes over different types of graphs and when you should maybe use them. First, we have the bar graph, and this shows the number in particular categories. A circle graph compares parts of the data to the whole. A double bar graph is good for comparing. Box and whiskers show measures of variation. A histogram is good to show frequency of data divided into intervals. A line graph shows change over time, and a line plot shows frequency on a number line.
So I'm going to leave it there, and so we're going to cover most of those things. So let's go and dive into our question. The first one is actually more basic, and that is our good old Venn diagram. So let's say we've got a group of things, people here, and what have we got? 20 students, 7 are taking maths, 3 are taking biology, 5 are taking neither. What's the probability of a student taking biology? Well, the diagram has 20 students, so how do we represent that? Well, this must be adding up to 20 altogether. And, of course, with the Venn diagram is maths on the left, biology on the right, and, of course, those who take both in the middle. That's pretty well understood by you, but you'd unpack that for your students. So the question asks, what's the probability of a student chosen at random in taking biology? Interesting, you may not have seen, that's the 5 students who take neither. So they're outside the circles. So taking biology. So the people in the biology are the 3 that take biology and maths, and the 8 that just take biology. So let's have a look at those. So the probability is the 3 and the 8 divided by the 20 overall. And that's 11/20ths. So that's linking probability with a diagram. But that's your Venn diagram makeup that is there. The other one is circle graphs, or pie graphs as they're referred to, and let's have a look at those. Now the trick is here that you actually have relative representation. So if you're doing a large audience or you're trying to communicate and report, pie graphs or circle graphs are really easy to see and easy to understand. It's very quick to see what's my most dominant parts. But it relies on the student's understanding that a circle has 360 degrees, and each sector of the circle has a certain number of degrees out of the 360 degree, and it's like as a fraction of it. So actually creating them and plotting them is a little bit more difficult for students, and you'd have to work those things through. Let's have a look at how you do that. That's explaining what our circle's about. Well, let's say we have 55% cheese, sauce, and pepperoni. It's a pizza one that is there. So, excuse me. So it's pretty easy to see that the cheese is one, ingredients. So that's moving on. Let's go through how I would use that as an example. So here's the data, favorite, lunches. And so we could organize it in a table as data is. Now we're going to need to convert that into a circle. The first step is create a fraction of the whole. Now let's have a look. I've gone one too far. So the first one is 10 out of 25, 8 out of 25, 5 and 2 in terms of the relative proportions that we have of our pizza, etc. So we're creating a fraction. And then the fraction can either be multiplied by 360 or converted to a decimal here in this instance, and then multiply by 360. Whether it's a fraction or a decimal, it doesn't matter. And that will give you your sector area. Notice that this one, 144, is much more significant, and that was the 10 out of 25, and that's the pizza, as you would expect. So if we go back, we see a different one here. Let's see where our result is here. There we go. But how do they go from that fraction or degrees. So they've got to get protractors, draw a circle, get protractor, map out 144 degrees, etc. Put a dot and measure it, and that would be your sector. And this is a very easy to see representation. Another one is what we call dot paths, which is the dot points or plots, which is the precursor to graphs, bar graphs. So here's some information, and you can see that's organized, and you might in your classroom get students to put dots in ascending order when they come across something which is common, and by that way they build up a bar graph physically. And from that you can see easily what's the tallest one, which is the most frequent, which is the shortest, which is the least frequent. You can have a range from going from 5 to 12, for example. So it gives you good information about what's much common and more frequent. And here's a video that you can look at. But here we go from a tally, okay, that is there, and a dot point, which is here. And we can see that each of one goes over there. So they've taken it from the tally and they've put it over to a dot plot. Now that dot plot, joining it up, we now have a bar graph, don't we, in terms of representing information. Let's go on. So the real question that I often get people to talk about is, do I do a bar graph or I do a line graph? Well, here is in the PowerPoint here, you'll see information about that, and it's a great video. But if they're separate categories, and let's have a look, and I'll move the screen down, apples, orange, bananas, they're not related in any way. The number of people who prefer it is a number, but those are separate categories. So if they're separate categories, they're never linked. And the mistake that often people make is they put a line and they join those things up to make a line graph. Well, if I reordered those fruit, the line would look different, wouldn't it? So it's not really valid to draw a line. It's actually valid to have a line graph. A histogram is another fancier term. It's a slightly different to a bar graph, but I wouldn't be worrying it at this point in time. The second thing is, however, if they're not separate categories, and they are sets of numbers, two sets of numbers. For example, here, cookie sales, and we've got time, haven't we? And that's a sequential, not a number, is it, by itself, but it is a sequence of time. You could say day 1, 2, 3, 4, 5, etc. So it's a period of time represented by and quantified with a word of the day and the number. So that is over time, and that represents. So although Monday, Tuesdays are different names, they're not numbers, they are a sequence of time which you could represent as a number. This one's over here. We've got here our dolphin, bears, etc. So you've got a time, which is a sequence of number, and you've got the amount, and therefore you're plotting those, and each of those is actually a multiple line graph with 3 different colors representing 3 different areas. That great basic line graph YouTube you might be interested in. Next is how is STEM, what we call STEM and leaf plots. Now STEM and leaf plots are really about organizing the information. It's a process that allows you to see, and it has a similar sort of feel to a dot plot. So let's have a look at those things, and here's the information that's there. So let's say we've got here's the points in a basketball game. Well, I've got lots of information. How do I organize this information? Well, here's one. Okay, so let's have a look at here. That's 110 and a 2. 110 and a 6. So when we have 16, it's represented by the 6 there. So we go through here and go 1, 2, 3, 4, 5. So that's 50 is the highest, and a teen area past 10 is the lowest. So we go through 20, and we would put a 7 there. Okay, 21st, there is there. So what you do is you plot all the information, and therefore you can read how much there is. So that organises, and you can see why most of the time we're going to hit the 20s as a basketball team. And so if you turn that on its side, it's a bit like a dot plot in some ways. But it also allows you, if you look at some of the videos, to therefore actually calculate a mean, your range of data, what's most frequent, your mode of data, and you could actually add it all up as well. So it organises, is a way of organising it. Now, the other simple organisation tools I'm sure you've had before is the mean, the averages. Well, there's 3 types of average, common averages anyway. The mean, which is the add all the everything up and divide by how much. In some ways, it's very useful. So if you've got a large bit of data, what's the average height of population in grade in a school, say, of 12-year-olds? Add them all up, divide by how many 12-year-olds. Really useful. But sometimes it's not so useful. If I said, okay, put your hand in the oven and put your other hand from your other arm into the freezer. Well, one is burning your hand off at, a couple hundred degrees. The other one is, minus 20 degrees. And then on average, you feel quite comfortable. Well, that's actually a nonsense now, isn't it? So sometimes mean averages are meaningful. So sometimes it's better to have a different sort of average. And a different sort of average is the next one, which is this one, have I? Mean. So also the range of your numbers is the lowest to the highest. Let's get the other one. The other one is the median. Excuse me. The median is the middle. So if you've got a range of things, what's the middle area? So if you've got a group of people in that class of 12-year-olds and you put them from smallest to the highest in that class, well, the middle person would be your average height for that class. It might not be the mean, if you add it all up and add them all up and divide by number of people, but if you could visualize all these different heights in the classroom, shoe size, it could be any bits of data, and the middle number, and I usually remember the median strip on the road is in the middle. So that's another average, quite valid average, particularly when you're looking at articles and stock and so on, as opposed to just a statistical measurement of adding things together. It might not be relevant. It's the middle one. The other one is mode. Now, mode is the most common number. So if you look at all those things here, for example, it's not great. If you're a shoe store owner, you want to order stock in, well, you're going to have a look at which ones are the most common. You buy more of the most common ones. You won't add up all your shoes and divide by how many shoes and say, okay, I'm going to buy 7.8 shoes. No, you'll buy ones which are the most common. You won't buy the ones that are in the middle because that's not meaningful. What are most people buying? So that's your mode. Here's an interesting one called the Box and Whisker Plot. Now that's more complex. You need to have a look at the video really carefully and go through those things. But this says, let's go back to a basketball performing type person and number of points in a game and say the lowest number for the season was down here. And the highest for the season was over here, 100. So 18 to 100 says that the range of your data. And what they do in the Box and Whisker Plot is divide everything into what they call quartiles. There's one quarter. So if you arrange all your numbers from lowest score for the season to the highest score for the season in order, and what is the middle number, the median, that becomes your halfway point. So that's halfway, and therefore that's your 0. So what's the middle of the lower half? Here is called the lower quartile. So you're breaking up, you're putting them all in order. Here's my middle, and here's my middle of the lower half, and my middle of the upper half. And what they put a box around between those middle of the lower and middle of the upper, and so that's your average range. So it's not a median where you add it all up and divide by per game, and that's a valid statistic too. It's not your median in terms of just the middle one. It's actually saying it's putting a box around and representing graphically that this is your normal range. So if you then got 65 as your score, that's within your normal. And maybe 80, again, that's in your normal sort of game that you might play as a team. That's if you score over here 95, that's in your upper quartile area. If it's less than the 50 odd, then it's actually below. So it gives a really good visual representation. And the next couple of slides go through that process for you. The last one is probability. I love probability. And what's probability all about? Let's have a watch at some videos.
Hi, I'm Rob. Welcome to Math Handies. In this video, we're going to learn about how to do math with things that only sometimes happen. They might be likely or unlikely. we're going to learn about probability. Usually in math, we deal with things that always happen the same way. They're completely certain. Like if you add 1 and 1, you're always going to get 2. If you multiply 2 and 3, you're always going to get 6. There's no uncertainty at all. But in the real world, things aren't always so predictable. Take a coin toss, for example. You can't predict whether it'll be heads or tails. It's unpredictable or random. That's why some people will flip a coin to help decide which of two things to do. That's how I make every decision in life. Why am I not surprised?
Just as likely, and there's only 2 sides to a coin. If we flipped a coin a lot of times, you should expect that about half the flips will be heads, and about half the flips will be tails. That means that the probability.
Even though we don't know what each coin flip is going to be, we do know a few things about it. We know that with a fair coin toss, that heads is just as likely to show up as tails. The probability of an event, like getting heads or getting tails, is a value that tells us how likely that event is to happen.
That's why the probability line
with our coin toss, since each side is just as likely, and there's only 2 sides to a coin, if we flipped a coin a lot of times, we should expect that about half the flips will be heads and about half the flips will be tails. That means that the probability of flipping heads is the fraction 1/2, and the probability of flipping tails is also 1/2. Let's look at this in a little more detail on something called a probability line. It's a number line that goes from 0 to 1. The probability of 0 means that an event cannot happen. It's impossible. The probability of 1 means that an event is definitely going to happen. It's certain. That's why the probability line only goes from 0 to 1. The event can't be less likely than impossible, and it can't be more likely than certain.
So you might expect
the probability of 1/2, like with our coin toss, means that an event is just as likely to happen as it is to not happen. Probability less than 1/2 means that an event is unlikely, and a probability greater than 1/2 means that an event is likely. Oh, and in addition to fractions, it's also common to write probabilities as decimals or percentages, since you can easily convert between them. The probability of 0 is the same as a 0% chance of something happening. The probability of 1/2 is the same as a 50% chance of something happening. And a probability of 1 is the same as a 100% chance of something happening. Now that you know how a coin toss works, let's see an example of an event that is unlikely, using something a little more complicated than a coin. Let's take a look at dice. A standard die has 6 sides, numbered 1 through 6. When you roll it, any of those sides is just as likely to come up as the others. That sounds a lot like flipping a coin, doesn't it? Each side of a die is just as likely to come up as the others, and each side of a coin was just as likely to come up as the other. So you might expect that the probability of rolling a 3 is 50%. But remember, with the coin toss, there are only 2 possibilities, heads or tails. With dice, there are 6 possibilities, and that's going to make a difference in its probability. One way to think about it is that it's certain that one of those 6 sides will land facing upwards, which is a probability of 1 or 100%. But since only one side can face upwards for a given roll, we have to divide up that value among all the possibilities. In the case of a coin toss, since there were only 2 possibilities, we had to divide the probability by 2. 1 divided by 2 is 1/2, which is the decimal 0.5 or 50%. But with the die, we need to divide the probability up evenly between 6 possibilities. 1 divided by 6 is 1/6, which is equivalent to 0.167 or 16.7%. That would be right here on our probability. That means it isn't likely that I would roll a 3, for instance. It's just as likely as rolling any other number. And since all 6 numbers have the same probability, each number should come up about as often as the others. To see if they do, I'm going to conduct some trials. That's an excellent argument. Allow me to deliberate. Guilty. Actually, in dealing with probability, a trial, which can also be called an experiment, is a process that has a random outcome, like tossing a coin, or rolling dice, or spinning a spinner. And the outcome of a trial is what happens in that particular trial, like flipping heads, or rolling a 3. So I'm going to conduct several trials by rolling a die multiple times and keeping track of how many times I roll each number. Aha! You said that each number was going to come up just as often as the other numbers. But look, there's more 2s than there are 5s. How do you explain that? Well, remember, We're dealing with things that are random. They're unpredictable. We can't know exactly what will happen, just what will happen on average. So now I have to calculate the average? Well, when we say on average, we mean that the more trials you do, the closer you get to the expected probabilities. Keep watching. There. Now that we've done a lot of trials, you can see that our totals are much closer to what you would expect them to be. I guess you're probably right. That's one of the really important things to keep in mind about probability. If you do just a few trials, the results might not end up very close to what you'd expect. In fact, they could be way off. But if you do more trials, you increase your chances of reaching the expected probabilities. There's another thing I should point out. Remember the probability of flipping heads is 1/2, and the probability of flipping tails is 1/2. The probability of rolling a 1 is 1/6, and the probability of rolling any other number on the die is 1/6. If you add up the probabilities for the coin flip, you get 2/2, or 1. And if you add up the probabilities for rolling the die, you get 6/6, which is also 1. And that's not just a coincidence. If you add up the probability
by the number of favourable outcomes over the number of possible outcomes, or the number of times the event will occur out of the potential amount of it will occur. And so it's this way here. Now that is classic examples I use using dice and coins and so on, but it applies to probability of any bit of information. So, the scale is, if it's a 0 chance or probability, it's impossible. It'll happen 0 times. And if it's going to happen every time, then it's certain. I don't know about theologically speaking, but is Jesus going to come back? I think it's certain. So that's a 1 out of 1 probability. But let's say you have an even chance of this. Okay, are you going to win that prize as, or something that's between the two of you and your pair? Well, there's an even chance, isn't there, perhaps? If it's better than 0.5, it's more than likely. And if it's less than 0.5, it's unlikely. And you've got those relative qualitative scales that those words might match the probability. But a probability of 1.0 is 100%, and it is absolutely certain. And we go 50-50, is 50% or is 0.5. So this is scale. And you can work out all those probabilities and have a look at the great videos that we have. But let's go through some information about probabilities by having a look at a video. Hope you enjoyed that video. It just really makes it clear about what probabilities. But there's interesting about what's called theoretical probability and experimental probability. So, and also two-way and other probabilities. So let's go and have a look at here. Now, experimental probability is the possibility of this occurring, but experimental probability is the actual data. So it might be that it would be 20% you would expect 0.2, but it actually is not. The actual result is 0.25. So experimental is actually the real life survey. This is what has happened as opposed to a theoretical one. So data was collected on people about their favourites. People, here they are, here's the data, boom, boom, boom. And Wonder Woman, Batman, Superman, total here, male, female, overall total. So that's real data. Now, because you've got real data now, that's experimental. You did an experiment, you surveyed, it was actual. Then you can use that probability to predict now as a theoretical assumption. So, for example, the Wonder Woman female said 62 out of the 100 preferred there. So 62% of females preferred Wonder Woman as their favourite character. Now, what is the chance that the next female will say Wonder Woman? Well, the chance is 0.62, 62%, because you've done an experiment on it. The theoretical probability could be 1 out of 3, because you've only given them 3 choices. What's your probability of this or this? Wonder Woman, Batman or Superman? They've only got 3. Statistically, they've got 1 chance out of 3. No, but the experimental probability said that actually it's bigger than that. Now, that experimental probability allows you to all the different factors of real life can influence. It's not just a free choice. There's cultural, there's, say, perhaps gender, there's personal preference, personality, or just a different area geographically will give a different result to another demographic group. So all those things are captured in experimental probability, not theoretical probability. Let's go on. And I'm going to have a look now at go on to a more complex one, is what happens if you have to use probability where there's two things happening. So let's use this example, Wonder Woman, Batman, and Superman. So what's the probability of a female who says, my preference is Batman, okay, and I'm over 55? So therefore we've got two things. The probability that the next person you sample will be over 55 and whether they have Batman. So it's the probability of Batman, and how does that relate to the probability of their age? Or it could be some other factor, not necessarily age, but say the person the male prefers Superman, and he also prefers to drive a red car. So what's the probability the person be a red car driving Superman loving male? So all those factors come into play. So they're multiple probabilities, and how does that look? So we're going to go to the video to finish this section. Like all our sections, make sure after you've done the fly-through video here, you go back to your Moodle site and go through the various aspects which unpack, give you examples, give you worksheets, give a little quiz at the end on all the factors that we've looked at today.
Die, and the second event is flipping a coin. Because the outcome of the first event does not affect the outcome of the second event, these events are said to be independent events. In other words, rolling a 6 doesn't increase or decrease the probability of a coin landing on heads or tails. The probability of getting heads is 0.5, and it stays that way regardless of what you roll. To calculate the probability of two independent events happening together, you can use this formula, where the probability of A and B is equal to the probability of event A times the probability of event B. Let's do an example. If you roll a 6-sided die and flip a coin, what is the probability of rolling a 5 and getting heads? The first thing we should do is write down the formula. But in order to use this formula, we need to know the probabilities of each event. If you watched the previous video, you should know that the probability of an event is equal to the total number of favorable outcomes divided by the total number of possible outcomes. For the first event, there is only one favored outcome, which is rolling a 5, and there are a total of 6 possible outcomes since we are rolling a 6-sided die. As a result, the probability of rolling a 5 is equal to 1 over 6. For the second event, we know that the probability of getting heads is equal to 1 over 2, or 50%. And we know this because there is only one desired outcome, which is getting heads, and there are a total of 2 possible outcomes since the coin can land on either heads or tails. Now that we have the probabilities for each event, we can use the formula, and all we have to do is multiply them together. 1 over 6 times 1 over 2 gives us an answer of 1 over 12. As a result, the probability of rolling a 5 and getting heads is equal to 1 over 12, or 0.0833. What are dependent events? Dependent events are simply the opposite of independent events. Dependent events refer to the occurrence of one event affecting the probability of another event. For example, suppose we have a box that contains 10 marbles. 7 of the marbles are green, and 3 of the marbles are blue. Based on this, we know that the probability of drawing one green marble is 7 over 10, or 0.7, and the probability of drawing one blue marble is 3 over 10, or 0.3. If we randomly select 2 marbles from this box, what is the probability of drawing a green marble and then a blue marble without replacement? A common mistake in solving this problem is by using the formula and then multiplying the probabilities of each marble together. So you'll have 7 over 10 times 3 over 10. However, this process is incorrect. This formula can only be used for independent events, and we know that this is not an independent event since the marbles are being drawn without replacement. The term without replacement means we are drawing the marble without putting it back into the box. This means that the probability will change after every draw. As a result, this is a dependent event, where the probability of one event affects the probability of another event. In other words, drawing the first marble affects the probability of the next marble. Let's see why this is. For the first event, there are 10 marbles in the box, and since we have a total of 7 green marbles, the probability of drawing 1 green marble is 7 over 10, or 0.7. For the second event, the probability of drawing a blue marble is not 3 over 10. Since there is a total of 9 marbles left in the box, with a total of 3 blue marbles remaining, the probability of drawing a blue marble is now equal to 3 over 9, or 0.33. As you can see, the probability of drawing a blue marble has changed. At first, it had a value of 0.3, but now it has a value of 0.33, or 3 over 9. As a result, this is a dependent event because the occurrence of the first event affected the probability of the second event. Now to finish this problem, all we have to do is multiply these two values together. 7 over 10 times 3 over 9 gives us an answer of 7 over 30, or 0.233. Let's do another example using the same scenario. What is the probability of drawing 2 green marbles without